paper. It's usually a small, like a ceramic kind of thing, or even glass, and it's coated with a powder. So they put the bottom in water. The water will flow up because that's capillary action. It'll flow up this thing through the let's say the thin powder layer. Again, the powder is like stuck to the glass, let's say, or the ceramic. So the water will flow all the way up. You put your sample right here. Let's say it's a component. As the water flows up, it'll carry the different components, some higher than others. Some will flow again. As the water flows up, or whatever the solvent is, as it flows up, it'll carry some component this much because that goes right there, and it'll carry this one even more because as the liquid solvent flows up, this one sticks a lot less to the film of powder that's, let's say, glued or stuck to the glass plate. So what can be done is, okay, you take your little spot over here, you put your tiny little solvent over here, or tiny little solution over here, put it in, let's say, a beaker of water or some other solvent, let's say acetone. It'll flow up. It'll carry, in this case, two other components, and there may be something left behind. So what you can do here is more or less, basically the main thing, possibly the only thing you do with this, is you see how many components are in there. You don't know how many components, but you see 1, 2, 3 spots. There are 3 components, so you don't have to worry about 3 of them. This is a very quick and general idea of what can be done with this thin layer chromatography. That's what we call it, thin layer chromatography. It's you get your sample. The initial thing is you put the spot on this plate, put it in a beaker of water, and you wait and you see, oh yeah, there are three things there. It must be 3 components. That's all you have to worry about. It could be 4 or 5, depending on how much stuff is in your sample. And that gives you an idea of what to worry about or how many things to worry about. It gives you a very general idea. You really don't really identify things very well with that. But again, it's a start. It's a quick and easy way of getting some information. So it's used. It's all used for generalized information, but as we mentioned. So that's thin layer chromatography. Okay, so now let's talk about the detectors. We mentioned that as your components pass the detector, it gives a signal. Now, what kind of detectors are there? The simplest ones use what they call UV vis absorption. That's ultraviolet visible. Let's use ultraviolet light or visible light, and it sees what is absorbed. Let's say you float through with water. Water does not absorb at the wavelengths that we're dealing with, but your components will. So you see when it's getting to be absorbed, you see, oh, something's coming through, it's absorbing. There's another that's fluorescence. The UV vis absorption, that's the most common one. Fluorescence, that's actually the most sensitive of them, not including whether you use mass spectrometry. We'll talk about that a little bit. We'll talk about that hopefully soon. But these are very sensitive. The way this works is you shine light on it, and you don't detect how much light gets absorbed, but your sample will absorb it, and it will actually give off light at a different wavelength. And we detect the light of a different wavelength, and we can detect it very well. And we can see if it's doing that, well, we know it's coming through. That's how a detector works. You shine light on it, we see it's fluorescing. It produces light at a different wavelength. We know it's producing light at a different wavelength. We know it's coming through. We have our signal. Here's an interesting one. Unfortunately, not many of them use this, but when they do, they get exact information out of it. This is when you shine an infrared light. You shine infrared light at the sample, and it'll get absorbed. But when you shine infrared light, not UV, not ultraviolet or visible light, but infrared light, that's light with a longer wavelength than visible light, and certainly ultraviolet light. You shine light on it, and it gets absorbed. But it doesn't get absorbed in, let's say, 1 or 2 bands. It gets absorbed in 50 or 100. Depending on the component, depending on the compound, it absorbs at many different places. And when you look at every different place that it absorbs, you can figure out exactly what the compound is. So not only from this kind of detector, not only do you know that something's coming through, you know exactly what is coming through. It's not that simple, but that's the idea. UV-Vis will give you a basic signal that something's coming through. Fluorescence will also give you a signal of what's coming through. IR absorption will give you a signal of what's coming through, but based on what gets absorbed, it's a lot of information what gets absorbed. It'll tell you what is coming through. We also have mass spectrometry. These are relatively common when they're combined, especially with gas chromatography. That's when the gas flows it through the column. So this is a different kind of spectrometry. We'll talk about spectrometry soon. But this is a different kind, and we'll talk about that later. What it does is it measures not just that something is coming through, that comes from these other detectors, but it's coupled with it, and it tells you the mass of what is coming through, as well as the mass of parts of what's coming through. But we'll see about that. We'll see a little more about that soon. The point is that the point is that it is a way of detecting what comes through and the mass of what comes through, and it is very often coupled with gas chromatography. So what the system is called GCMS, gas chromatography mass spectrometry. Okay, that's the MS for the mass spectrometry. Okay, so let's take a look at how they sort of work. We have the UV-Vis detector, absorption of ultraviolet or visible light, and you can tell it, you can feed this thing different kinds of light, different wavelengths, ultraviolet or visible, and different kinds in between. This is the most commonly used. The idea is light hits your sample. Here, let's say it's flowing through from up to down, or who knows how it's flowing through. The point is you've got it flowing through, let's say, a quartz part over here. Light, and you can sometimes decide which wavelength of light you want to shine through it. So anyway, you shine light through it. It will hit your sample, and your components will absorb light. Will absorb some of it. What gets through it is a less intense beam of light. Your detector will detect, it says, I know the strong beam of light hits it. I'm suddenly getting a lot less light. That means someone's getting absorbed. So it gives you a signal of, we have just absorbed this wavelength of light. That tells you your component is going through. Now, the eluent or the solvent that you're making the flow right through it, or the gas that makes it flow, either way, will not. You will not absorb light at the frequency that you're using. So then it'll give an ordinary strong signal. It'll go straight through. Then when your component starts getting through, the parts of the different molecules will start absorbing it. So your wavelength light will not get through all the way. It'll be weaker. Your detector will detect the weakness, and it'll show up as a peak in your chromatogram over here. That's how the common UV-Vis absorption detector it works. There's the fluorescence. Now, fluorescence is usually, remember, the lights, what's happening is the light hits your, let's say, as it's flowing in whichever direction, at a 90-degree angle. I can't show it really well in the picture, but let's say the 90-degree angle will hit your detector. Remember, the light is hitting whichever specific wavelength, usually ultraviolet or visible, but not infrared. That we'll get to soon.